what is the condition? What is the condition for this? So the question is, we need to find out the distance that this person has climbed along the ladder before it slips. Okay, so this is a problem about equilibrium. What are the conditions for equilibrium? Anyone?
The resultant forces are zero, angular momentum is zero, and
two things. Okay, two things. The sum of all the forces should be zero, and sum of all the torques should be zero. Okay, these are two conditions: sum of all the forces and sum of all the torques. If both of these quantities are zero, then the ladder would be still in equilibrium. So we would use these two conditions. So for that, we need to identify all the forces acting on this ladder and all the torques. All right, so let's begin with the forces. And maybe I could just use a different colored chalk here to identify the forces. So one of the force is MLG, right? The weight of the ladder acting at the center of the mass of the ladder. Okay. We assume that the ladder is constructed in such a way that its center of mass is at L/2. L is length of the ladder. Okay. This is L. Right. So one force. Another force here is the force of friction in this direction. Let's call it F. Okay. Another force somewhere, depending on the position, is the force of the painter downwards. Okay. Let's call that this MPG. Okay. So two forces downwards, one force leftwards. Now, of course, this ladder needs a normal force. So the ground is exerting a normal force upwards here. And let's call this NY. Okay. Why NY? Because I have another normal force, so I don't want to use just N. Okay. And here, since there is no friction, so there is no force upwards. All right. And there is normal force that the wall is exerting on the ladder in this direction. Let's call this NX. Okay. So 1, 2, 3, 4, 5 forces. Okay. Do you see any other force that we have not accounted for? Sometimes this problem is given in a bit more complicated shape, that you actually have this mu non-zero. If this mu is non-zero, then possibly the ladder could slide downwards or is trying to slide downwards. So there is a force of friction acting along this surface, okay, in that direction, sorry, between these two surfaces here. But we are given this, so we don't need to consider that force. Okay, now just let's write these forces in our coordinate system. So we can choose the coordinate system to be like this: EY and EX. Okay, and first we can write the X component first. Okay, what would be the X component? What are the forces acting along X direction? Only two forces are acting along X direction, no?
Is it F and NX?
Yes. Yes. So NX be positive. Okay, and F would be negative. And since it's a vector equation, this one, all components should be 0. So this should be equal to 0 for the equilibrium. Okay. Now equation in the y direction would be what? Ny minus mlg minus mpg, right, equals 0. So we got two equations from the forces. Okay. And now we go back and we write we do the same thing for the torques. Okay. Since there are 5 forces acting on this system, there would be 5 torques possibly that we need to account for. Okay. And they would be torque due to, let's start with in this order, torque due to Nx. I'm using the forces as sub labels to indicate which force is causing this torque. Okay. And torque due to the force of friction, then the torque due to normal force Ny, then the torque due to mlg, okay, then the torque due to mpg, and all should be equal to 0. Okay. So let's find out all these torques. Okay. What would be the torque due to Nx? Anyone? I have to say, you have to assume a point of rotation. Okay. Let's say that we are considering, or you have to assume a point, you have to mention a point around which you are calculating the torque. So we're calculating the torque around center of mass, L/2. Okay, along the ladder. So what is the torque due to this force?
Sir, ये angle कितने का बन रहा है?
Oh yes, I forgot about that. This angle is theta, and it's actually given. So theta is given, it's 30 degrees. Okay, but let's just write for now, let's keep everything symbolic. So what is now you know theta. So what is the torque due to Nx?
Sir, Nx cos theta L/2.
Nx cosine theta L/2. Yes, that's right. How did you get it?
Sir, वो resolve किया था पहले उन्हें और फिर distance from R ले लिया directly.
Yes. So if you resolve, so this distance is L/2, right? And if you resolve it in 2 components, okay, this is the vertical distance between the point where force is acting and the point of rotation. And this distance is L/2 cosine theta. Everyone agrees? And then you just take, and one more thing, what about the sine of this torque? Okay, this distance, okay, and the torque is acting in this direction. So which direction the force is in this direction and the distance is in this direction. So what would be the direction of torque?
Into the plane.
Into the plane. So that means negative.
ये से negative हो जाएगा.
Yes. So that would be Nx L/2 cosine theta. Okay. What about the torque due to the force of friction, F?
सर आपकी स्क्रीन स्टक हो गई है।
Is it okay now?
ये सर अब ठीक हो गई है।
All right. So what is the torque due to the force of friction? Hmm?
सर वो भी एफ L/2 cos थीटा ही हो जाएगी।
Be careful with that. Okay. This is the force of friction. Okay. And this is the vertical distance. And what is this? What is this distance?
सर L/2 cos थीटा।
ठीक है, ठीक है, ठीक है, ठीक है, ठीक। Yes, yes, yes. And what about the direction of the torque?
सर ये पॉजिटिव हो जाएगी, आउट ऑफ द प्लेन है।
Wait. क्यों? देखें, अगर आप राइट हैंड रूल लगाएं तो ये फिर भी अंदर ही जा रही है, डायरेक्शन टॉर्क के अंदर ही है,
ये सर इनटू द प्लेन ही है।
into the plane here. So we keep the same sign. Okay. F L/2 cosine theta. Okay. How about the torque due to Ny?
सर Ny L/2 sin थीटा।
Yes. So this is Ny acting in this direction, and vertical distance from the point of between the point where force is acting and the point of rotation is L/2 sine theta. And now this is counterclockwise. Okay. So this would be, sorry, I should have written both of these negative, no? That's what we decided. So they are into the plane. So both of them are negative. And now that is out of the plane. So that would be positive. Ny L/2 sine theta. Okay. Now one more, two more forces to go. Okay. So what about the torque due to the weight of the ladder?
सर जीरो हो जाएगा।
0, because it's acting at the center of mass. What about the torque due to the painter, the weight of the painter?
सर ये वेरी करेगा डिस्टेंस से।
Vary करेगा. So let's introduce the variable. Okay. Let's say carefully that the distance between the center of mass, okay, the position of the painter with respect to the center of mass is K. Let's call this K. Okay. Standing here, and so depending on its value of K, this torque would be different. When the painter is exactly at the center of mass, torque due to its weight is 0. When it is below, the torque is in this direction. Sorry, the torque is into the plane. Is that so? Yes. And when it is here, okay, then the torque would be out of the plane, or the other way around. Just make sure that we are
ये सर पहले इनटू द प्लेन और फिर आउट ऑफ द प्लेन है।
okay. So the torque changes its direction. So the last term, this is 0, and the torque due to the painter would be simply mpg k. No, यही होगा ना? Oh no, but you have to be careful. Sorry, with this would be again, if the distance between the painter and the center of mass is k, then this would be
K sin
mpg
थीटा हो जाएगा।
k by 2, right? Would it be k by 2 or just k?
फिर वो sin 30 मेरे ख्याल से हाफ आ जाता है, उसकी वजह से K/2 बन जाता है।
Yeah, but wait. So you have, Yes, it doesn't have to be, I think, k by 2. It's just if you keep it k, then the vertical distance between the point of rotation and the force is k sine theta, right? All right. So these are all the torques and they have to be 0. Okay, so now let's see if we can solve this equation, solve these equations. We know, what do we know here? We know Ny, because we know both the weight of the painter and the weight of the ladder, okay? So from here you can calculate Ny. कितनी होगी क्या Ny? करके बता सकते हैं जल्दी से?
Sir, 700 आ रही है मेरे ख्याल से.
700 Newton. So I'm just so Ny is 700 Newton. Once you find Ny, then you know that F, then
F
you
भी आ
know,
जाएगा,
right?
sir.
Because F is simply mu Ny. तो F कितना आ जाएगा यहाँ से?
Sir, 245 आ रहा है.
245. So you find F. So 245 Newton. Once you have found F, then you can find Nx. That would be the same, no?
Sir, वो भी 245 आ गया.
वो भी 245 हो गया. And once you have found Nx, now look at this equation. Okay, you know Nx, you know L, you're given theta. L and theta are given. Here again, you know F, L and theta are given. You also know Ny, L and theta are given. M, P, G, sine theta, you know. You can calculate K, right?
Yes, sir, आ जाएगा क्या?
ठीक है? So just calculate K, okay? And be careful. If you calculate K, the K, I have taken it to be positive in this direction. So even if the K can have any sign, if particularly if K has minus sign, then it's fine because that is indicating that the painter is on the other side of the center of mass. Okay, but then K is the position with respect to the center of mass. If you want to calculate how much distance, how much length it has climbed along the ladder, then you must add this distance L by 2 into whatever distance you get here. ठीक है? Most likely it would be larger than L by 2. Okay, whatever value of K you get, you add it to L by 2 and you will get, and most likely the position of the painter would be somewhere here. ठीक है, ये कर लें जरा, खुद ही कर लें.
सर, एक सवाल पूछना था. हम ये क्यों नहीं करते कि टोटल डिस्टेंस जो वो पेंटर ने ट्रेवल किया वो ले लें और फिर L-2 माइनस टोटल डिस्टेंस करके निकाल लें
जैसे मर्जी
K
कर
की
लें.
जगह.
हाँ, क्या आप क्या लिखना चाह रहे हैं K को?
K को ले लें टोटल डिस्टेंस ट्रेवल फ्रॉम बॉटम जो पेंटर ने ट्रेवल किया और फिर वो हो जाएगा L/2 माइनस K करके.
Yes, but then look, then the problem is then you won't get the simple expression for the torque. Then torque की थोड़ी ये complicated हो जाएगी ना. वो एक ही बात है. अगर आप ये कह रहे हैं कि आप ये कह रहे हैं L minus K ले लूं,
ये
ये
सर
ले
ये
लूं,
इस तरह करके.
ठीक है, ठीक है, ऐसे भी कर सकते हैं, वो कुछ नहीं होगा. ये तो चॉइस है. आई थिंक दिस वाज अ सिंपलर चॉइस.
ठीक है सर.
ठीक है, but you can do it that way. I think you'll get the same answer. Find out K yourself. So this is how you solve the problems of equilibrium. Okay, any questions so far? Okay, the second problem is the oldest artificial satellite still in orbit is Vanguard 1, launched on March whatever. Its mass is 1.6 kilograms. Neglecting atmospheric drag, the satellite is still in the orbit with a minimum distance from the center of mass and speed at this perigee point of 8.23 kilometers per second. For this orbit, find the total energy of the satellite Earth system and the magnitude of the angular momentum of the satellite. Okay, so we have Earth here and a satellite going around. Now, the first law, Kepler's law, tells us that it would have an elliptical orbit. Okay, this is the best I can do drawing an ellipse. So I hope you understand that it means an ellipse. Okay, so and there is a satellite of its given mass 1.6 kilograms. Okay, and at perigee, so there is this new term I'm sure most of you are familiar with. This is, and this then is apogee. For satellites or planets on elliptical orbits or on actually any type of orbits, the point where a satellite or a planet is closest to the object that it is going around is called perigee, and the point where it is farthest from that object is called apogee. Okay, and now satellite at this point, at shortest distance from Earth, we are given this distance, we are given L. Okay, and this L is 7.2 10 to the power 6 meters. Okay, and at this point its speed is 8.3 kilometers per second. Okay, so the first part is to calculate the energy of total Earth satellite system. Okay, whenever you're given a problem like this, you have to define a reference. Okay, since if we choose the reference point to be Earth, then Earth's own kinetic energy, Earth's energy in a frame of reference which is resting on Earth would be 0. So there would be no kinetic energy to account for. Okay, there would be no potential energy as well, because that is where we set our origin. Okay, that is where we are measuring it from. We set the 0 of the potential energy at the position of Earth. Okay, so we don't really need to account for Earth's energy. All we have to worry about the energy of the satellite, both the kinetic and the kinetic energy and the potential energy, and there would be a just that. I mean, so you can look at, say, you can look at this energy either as as rotational kinetic energy or just kinetic energy, because its velocity is changing. So you would just get these two terms. The total energy of the satellite would be the kinetic energy of the satellite and the potential energy of the satellite. So how do we calculate these two quantities?
Half mv square and gmm over r.
G?
हाफ एम वी स्क्वायर से काइनेटिक एनर्जी आ जाएगी और जी एम एम ओवर आर से पोटेंशियल आ जाएगी.
Yes, half m v squared. All right. And potential energy कैसे आएगी?
फिर जी एम एम ओवर आर से आ जाएगी.
कैसे कैसे दोबारा बताएं?
फिर जी एम एम ओवर आर से आ जाएगी ना, मास ऑफ अर्थ एंड मास ऑफ सैटेलाइट ओवर डिस्टेंस एल.
Yes, but let's see. So this is so before so let me just complete this. The problem is this, that we only know the velocity at this point. Okay, and we only know the distance at this point. Okay, what happens when the object is here?
सर उसकी मेरे ख्याल से वेलोसिटी इंक्रीज हो जाएगी और पोटेंशियल एनर्जी डिक्रीज हो जाएगी. बल्कि
But this
पोटेंशियल एनर्जी
so since it's a conserved system, if we can calculate its total energy at this point, then we don't really care about the details, that how much of the total energy is into kinetic energy at a different point and how much is the potential energy. The sum would remain the same, although these individual contributions would change as it goes around the orbit. ठीक है?
ठीक है सर.
Okay, so the potential energy, usually if we were close to the surface of Earth, we would just simply write MSGL, right? But we now can't write that because G is the gravitational acceleration close to the surface of Earth. Okay, so we have to write or if you want to be more rigorous, you can also calculate the amount of work that you would need to do, okay, for taking this planet from 0 to distance L from Earth, okay, and then this would be the force of gravity, dl, okay. And if you do this integration, you will see that the answer turns out to be the work that you need to do would be with probably a negative sign because you are working against the force of gravity, and that's fine because the negative. So the work done by the, yeah. So don't worry about the sign, okay. If you do this integration, you would get GMS ME over L. Okay, this would be the potential energy. And if I could just simplify it, I could also write it as MS G ME over L squared into L. Okay, we get exactly the same thing, but this is nothing but the acceleration due to gravity. Okay, but anyway, so doesn't matter whichever expression you want to write, you can calculate the potential energy where A is this MS and L. And you can find out now E, the total energy, because you know the mass, you know the velocity, you know L, you again know mass, and in the acceleration, you have everything that you know, the gravitational constant, mass of Earth, and L. This would be the total energy. Okay. Now it asks you again the angular momentum. The angular momentum would be, again, angular momentum is a conserved quantity. Okay? If we just calculate it at this point, it would remain the same, okay, everywhere on the orbit. So this is how you calculate angular momentum, right? L cross P, they make the linear momentum, and L make a 90-degree angle. So just LP, and you know everything here, right? You know L, you know MS, you know VS. So you can find the angular momentum like this. And the last thing is to find the, what is the last thing? Find the semi-major axis of its orbit. Okay, so the semi-major axis is half of this distance, no? This is semi-major axis, A. So it is asking us to find it. There is something before that, right? Yes, there is part B, which says at apogee, find the satellite speed and its distance from the center of Earth. So we need to find out V, and K. K is the distance from Earth to the farthest point, and V is its speed at the farthest point. Okay, so how do we do that? We use the conservation of energy and conservation of angular momentum. So it's position K at the apogee and momentum at the apogee. That is what we need to find out, but they would be equal to L, the same thing that we calculated before, okay? And the kinetic energy would be half ms v at apogee, again, VA squared plus m s K A K P. Oh, sorry, K A P A. Okay, that would be its total energy, no? Oh, sorry, this is acceleration. MSA and Ka. And this is total energy. Okay, so if you look at these two equations, we have two equations and two unknowns, Ka and Pa, but you don't see Pa here. Eh? You can rewrite the kinetic energy as Pa square over 2m plus MSA Ka equals E. Okay. You can solve these two equations simultaneously to find Pa and Ka. Okay, so this is another part. And the last part asks you to find the semi-major axis of its orbit. So by now, we know Ka and we know L, okay? And that is equal to 2A. So from here, you can calculate from L plus K to A, and just don't confuse this. A is the length of the semi-major axis, okay? I don't confuse it with the acceleration. So from here, you can calculate A and determine its period. Also, the third law, the Kepler's third law gives us this relationship. The square of its period is equal to 4 pi squared GME A cube. Okay, where A is the semi-major axis. If you know semi-major axis, you can calculate the period. Okay. Any questions so far?
सर ये सेमी मेजर एक्सिस क्या है, ये थोड़ा एक्सप्लेन करते हैं.
Semi-major axis is half of this length, the half of the distance between vertices of an ellipse.
ठीक है सर.
All right, so okay, what is the last problem? The gravitational force on body located, etc., etc. Well, essentially, let me just quickly make this point. So okay, it's not a very good picture, but anyway, it serves the purpose. So this is Earth, okay, and we have cut a hole through its center, okay, all the way, created a tunnel out of it. Okay. Now, if you jump here, okay, want to find out what happens to you, okay. So this is the question that we are trying to answer. What is the gravitational acceleration? I'll just redo it because we have been doing it. So this is how you figure out G or the gravitational acceleration. You say F is equal to ma, right? And when the force is due to the universal force of gravity, then you get me m over re squared is equal to ma, and m cancels, and this is how you get the acceleration. Okay, g me, okay, over r squared. But this is on the surface of Earth. Okay, what would be the acceleration as you go down? Let's say this is the center and you're standing here. What would be acceleration at this point? Would it be this same?
नहीं सर, डिफरेंट होगी.
कैसे वो कैलकुलेट करेंगे?
सर हम वो सेंटर से डिस्टेंस मेजर कर लेंगे ना, और फिर इस इक्वेशन में आर की जगह उसको उस वाली वैल्यू को पुट कर देंगे.
ओके, कभी कर देते हैं. लेट्स से कि सेंटर से डिस्टेंस है स्मॉल आर. ठीक है. सो नाउ द एक्सेलरेशन इज GME R square. ठीक है, तो ये ठीक है.
ये सर ठीक है.
There is a problem with this because if you go down, the further inward you are going, your acceleration is increasing.
सर वो मास उसका चेंज हो रहा होगा अर्थ का.
Yes, so this is very important that the relationship is true, but you have to change the effective mass. When you're at the surface of Earth, the effective mass of the Earth that is providing the gravity, as if all the mass was concentrated at the center of mass and acting on you, was the total mass of Earth. But if you have moved a certain distance inside, now only this part of mass, because this mass has been left out. This does not exert a force towards the center of gravity, towards the center of mass of Earth. Only this would be the effective mass within that radius that is pulling on you. Okay, so we need to rewrite this expression for the acceleration in terms of an effective mass. Okay, that would be correct. So G M effective, okay, over R square. So how do we calculate M effective? That's not very difficult. Okay. So this is how we calculate M effective. So let's say first, let's calculate the density. Let's say the Earth is a sphere of uniform density, okay, assumption. So the Earth's density would be ME over 4/3 pi RE squared. Okay, that is Earth's density. Now effective mass would be rho E, all right, multiplied by what?
V effective over
V
4/3
effective,
pi.
V effective, yes, very good. So V effective would be 4/3 pi small r cube, right? यही होगा ना V effective.
ये सही आ गया.
ठीक है, so that is M effective. So then the acceleration becomes,
सर हम वॉल्यूम ऑफ अर्थ से नहीं डिवाइड करेंगे? नहीं बल्कि ठीक है
वो तो डेंसिटी में कर दिया ना यहाँ पे.
ठीक है सर, समझ आ गया.
तो अर्थ की डेंसिटी टाइप द इफेक्टिव वॉल्यूम. ठीक है. So then we have GE. Okay, we plug in everything here. Okay, GE rho E four by 3 pi R cube. Okay, over R squared. ठीक है. Then this cancels with this one, and let me just substitute the value of rho E here as well explicitly. Okay, so we get GE ME over 4 by 3 pi RE cube times four by 3 pi R. So this cancels 4 by 3 pi R here and here cancel. And we are left with GE ME sorry, this I don't know why I should have wrote GE. No need to write GE. GME RE cube times R. ठीक है. I can rewrite this further like GME over RE square R over RE. Now what is this?
ग्रेविटी आ गई G.
Small g. So I wanted to, now we can write the acceleration as A equals G R over RE. Now this makes much more sense because when you are at the center of the Earth, the effective mass that is providing gravity is 0 and the acceleration is 0. Okay, and when you are at the surface of Earth, this R is equal to RE and you get G back. ठीक है?
ठीक है सर.
Okay, then the rest is much more easy. Now, what would be, so on this side, we have the force of gravity. Oh, sorry. Now see this. I can equate the force with mass time acceleration. Okay. And let me make another assumption here. So I take my origin at the center of mass of Earth. So R is pointing upwards outside the center of mass. So this acceleration would be negative while going towards the center. Okay. When it goes away from the center, it is positive. When it goes towards the center, it is negative. Okay. So that means this acceleration is negative. Okay. Now F is equal to ma, and A I know is minus mg over RE into R. Okay. Now look at this. F is equal to, this whole thing is nothing but a constant, no? So can I write it like this? KR, where K is mg over RE. See this equation? Looks familiar?
Hooke's law की आ गई.
Like a spring. That's exactly what happens if you cut a hole through the earth and jump into it. The force due to gravity on you would be just like a spring force. You would be oscillating back and forth. As you would reach the middle of the earth, the center of the earth, you would be moving the fastest. And as you start going away, the earth tries to slow you down because the effective mass is increasing. So the force inwards is increasing due to the effective mass that is pulling on you. So you slow down, and by the moment you have arrived on the other end of the earth, your velocity is zero. You have slowed down to zero and you start falling down again. Okay. And you would be a simple harmonic oscillator going through the middle of the center of the earth. So you can solve the rest of the equation. I'll just paste some important quantities here. For example, the frequency of that oscillation would be you can calculate K over M, and it turns out to be G over RE. Okay, that would be the frequency of oscillation. What about the period of oscillation? How long would you take? Okay. T 2 pi RE over G. Okay. And you see this, you know everything in here. Basically, you know the radius of Earth, you know G, you can actually calculate. Yeah. I forgot to print the numerical value. I think, yes, I don't have it here, but it's close to 80 minutes, 84 minutes or something. Just check. That is how long it would take any object. You see that period is independent of mass. It only depends on the radius of the planet, whatever planet you're cutting the hole through, and the acceleration due to gravity at the surface of that planet. Okay, so this period is not really determined by how heavy the object is that you're throwing in. Okay, so it should be same whether you throw something small or something very big. Okay, now there is one more part to this problem. And the next problem is that they want you to calculate if instead of jumping through the earth, if you were going around just at the height of, just around at the surface level of earth, if you're going around, what would be the period of circulation or period of rotation? Okay, so we need to calculate and compare it with this value. How do we do that? So we have a force that produces a centripetal acceleration. Okay, the force we know is mg, okay, because we are at the surface of earth, and we know that centripetal acceleration is v square over re, right? And from here you can calculate v. What would be the speed? Anyone?
Square root g over re.
स्क्वायर रूट आर जी होगा ना, आर इधर आके मल्टीप्लाई हो रहा है.
ये सर स्क्वायर रूट r e g हो जाएगा.
ठीक है, so that's v. Now if you are going around a sphere of radius re, okay, what would be the period if you know v? How long would you take to go around it?
So 2 pi over t आ जाएगा, 2 pi r over t.
Yes, ये बिल्कुल ये ना, s is equal to vt and t would be 2 pi re over reg, right? तो ये क्या आ गया टाइम पीरियड? तो सिंप्लीफाई करें, स्क्वायर रूट reg नीचे है, ऊपर 2 pi re, ये क्या हुआ?
सर 2 pi square root r e over g.
2 pi square root re. Now that is the period if you're going around the earth. That's how long it would take. And look at this one, they're the same. Is it surprising or
third law से भी हो
expected?
सकता है ना?
I don't know, probably yes, because if you know, yes, you can do that. Yes, if you know the length of the, yeah, basically you know the radius. In this case, radius is the semi-major axis. If we are assuming a spherical orbit, or sorry, a circular orbit. Anyway, but you get the same time period, and this is important. This is to make a point that the circular motion and oscillatory motion are independent, are intimately connected. Okay, and that is to say that's why the period is same. And you see that when we did the harmonic motion, we get angular frequency. And how are they same? It's interesting. If you have an object going on a circle, okay, and if you shine light up here vertically and see on the ground shadow of this object, okay, if an object is moving with a constant angular speed in a circle, its shadow on the x-axis would execute simple harmonic motion. Okay. Similarly, if you shine light here, okay, the shadow of this object on this screen would make a simple harmonic motion. You can even write these equations. So it would be x would be simply r cosine omega t. That would be x. Okay, if r is the radius of this circle. and y would be r sine omega t. Okay, and these are basically the coordinates of this particle. If you square them, you get the motion on the condition for the motion on the circle. So the circular motion and the oscillatory motion are intimately connected. Okay, so this omega and this omega would be the same exactly. All right, and so now we are almost at the end of this course, and we have been looking at different types of motion. So one of them was, the first one was translational motion. The second one was rotational motion. And the third one that we are now learning about is oscillatory motion. An automobile is a perfect example of all three types of motion being connected to each other. For example, if you know how engine works, so you have piston, right, going up and down, doing oscillatory motion. Okay, connected with the piston, you have crankshaft. Now, crankshaft in this whole design is changing the oscillatory motion into rotational motion. Okay, then from crankshaft down to your tires through the transmission system, everywhere you have rotational motion. And then somewhere in the automobile, you have tires which are rotating. But the whole automobile itself is doing a translatory motion. So tires are basically helping you convert the rotational motion or the rotational kinetic energy into the linear motion, into the translational motion. So you see all three types of motion are connected to each other. An automobile engine and automobile itself is a perfect example of that. Okay, thank you very much.
सर वो मैंने पूछना था कि